We've really spent a lot of time talking about the natural numbers in this class and in this number theory portion, and really that's kind of the goal. But the natural numbers, in some sense, make up a lot of other things. And so we have, if you consider the natural numbers, we've seen the set 1, 2, 3, 4, and so on. If you were to just add the number 0 to that, you would get what we call the whole numbers. Okay? The whole numbers are just 0, 1, 2, 3, 4, and so on. And then, of course, if you were to include all of the negative version of the natural numbers, you get what we call the integers. The integers are all of the numbers that are basically, we get the positive, the natural numbers, we've got 0, and we've got all the negative natural numbers. So all the, like the mirror image of the natural numbers, but less than 0. And so because those go indefinitely to the left, I go dot, 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 comma, -4, -3, -2, -1, 0, 1, 2, 3, 4, dot, dot, dot. And so we have the positive side, we have the negative side, and 0, all included. Those are the integers. Now, some people will call the natural numbers the positive integers. Okay? So these are AKA positive integers. Oh, I can't spell integers apparently. Integers, ERS, right? There we go. Positive integers are the natural numbers. So we have the positive side, we've got the negative side, we've got 0. Now we can also look at fractions or ratios of integers. Okay, so we take these integers and start putting them in fraction form, saying, 4 divided by 2, well, that's 2, it's back in there. But what if I did 3 divided by 2? Well, that's not back in that set, so there's not closure here with regard to division. What we do have is 1.5, which is in between 1 and 2. And so we have a set of numbers called the rational numbers. The rational numbers are essentially all values that look like P over Q, such that P and Q are in, the integers. I'll just say P and Q are integers. And there's one other little tidbit here. So P over Q creates a rational number. That's a fraction, right? Ratio, rational, ratio is fraction. However, the denominator cannot be 0. If you recall, division by 0 is undefined. And so I also have to have Q not equal to 0. Okay, as long as the bottom is not 0 and the top and bottom are both integers, then you have a rational number. Negative 54 over positive 13, for instance, is a rational number. Okay, so we've got natural numbers, whole numbers, integers, rational numbers. Make sure I'm not missing anything. Okay, and so there's one other set of numbers, because this set of rational numbers doesn't hit everything, right? There's other things out there. So the question is, what about things that aren't in there? Things like pi. You may have heard of pi before. It's what we call an irrational number. And there are many other irrational numbers. Irrational numbers, if I was to describe them, it's not very easy to describe. I mean, other than you can't write them as a fraction containing integers. And so what we want to do is another representation of fractions is decimals, right? Well, the integers have what we call terminating or repeating decimals. R-E-P-A. Having a hard time spelling right now. E-T-I-N-G, repeating decimals. Okay, so terminating would be like your 0.25, right? 1/4. That's a terminating decimal. Writing everything on a slope here. There we go. 0.25. That's terminating, right? That's equivalent to the fraction 1/4. Repeating decimals. Well, something like 0.7 repeated, 0.77777 indefinitely. Well, that is a fraction 7/9. Okay, and there are many such fractions. I'm not going to have you do a lot of conversions here, but these are things that are rational numbers. They have either a terminating decimal. It could go out 50 digits before it terminates, but that's still rational. Or repeating decimals. It could just be the 1 digit repeating, or you could have 15 digits repeating. It could be the same 6 digits. 583241, 583241, 583241, so forth. That was 6, yeah. And so anytime there's a repetition, an infinite progression of that repetition, or a termination, it's a rational number. Therefore, the irrational numbers must be things that don't fit either of those categories. Okay, so irrational numbers are numbers that kind of are in between the rational numbers. They're not rational. They've got decimals, and the decimals keep going on and on. But they're also on a number line, just like all these other ones, right? So the number line, if you think about this, called the real number line. It's like a giant ruler or a giant tape measure that's infinitely long. And every number is a point on that line. The rational numbers don't take up every point on that line. In fact, they don't even take up the majority of the points on that line. Whatever majority means when you have an infinite number of them. The irrational numbers take up the rest. And these are numbers that are neither terminating nor repeating decimals. Okay, that's maybe the easiest way or most brief way to explain them. There are many very convenient and useful and common irrational numbers. The number pi is a big one. That is, for any circle, it's the circumference divided by the diameter. Okay, if that ratio then is irrational, then it must be the case that one of the two, either the circumference or the diameter, must also be irrational. Okay, because you can't have a fraction made up of integers making pi. So if it's defined as a fraction, one of the two parts has to be irrational. So pi is irrational. The number e, if you've ever heard of the number e before, it's a very interesting number that deals with exponential functions and kind of some really neat applications. We'll probably see this when we get into financial math. But the number e is very great for uses in compounding interest, population growths, other things. So that is a really cool number. And then things like the square root, all of your square roots of non-perfect squares. So like square root of 2, square root of 5, square root of 12. Those are all irrational numbers. The cube root of 7. Okay, roots of things that are not perfect squares and cubes. Those are irrational as well. You can construct those geometrically. If you had the square root of 2, if you had two sides of a triangle that were each of length 1, a right triangle, then the hypotenuse is length square root 2. So a lot of these show up in geometrical applications, and you get some pretty cool behaviors and properties associated with them. Now, if you think about all of these, they all make up what we call the real numbers, okay? And I'm going to create now what we call a Venn diagram, sort of, to represent the real numbers. And so the real numbers are represented by a capital bold R. Okay, typically we use that notation for the real numbers. And the real numbers encompass all of these other ones that I was just talking about. If you were to think about all of the real numbers kind of as your universe, there it is, then within that set are two main disjoint sets. They are the irrational and the rational. Now, the irrational numbers actually are significantly greater in size or cardinality than the irrational, okay? So what I'm going to do is split this into two regions. There's the irrational numbers, and I'm giving them a larger chunk just because it's a bigger set. There's actually more irrational numbers than rational. And then over here are the rational numbers. Okay. Within the rational numbers are the integers, right? So in here somewhere, we have the integers. Right? Those are a subset of the rational numbers. So all integers can themselves be made by fractions of other integers, right? The number 2 is, I don't know, 6/3, right? You can create them using fractions. The integers are kind of a superset of the whole numbers. So remember, the whole numbers are inside there. And of course, the whole numbers contain the natural numbers. In fact, the only number between the whole numbers and the natural numbers is the number 0, right? Then you just tack on the number 0 to the natural numbers to get the whole numbers. But anyway, that gives you kind of a Venn diagram showing you how these number sets are related to each other. Certainly we have relationships like the natural numbers are a subset of the real numbers, right? And so forth. Natural numbers are a subset of the whole numbers are a subset of the rational numbers, all that stuff, okay? So lots of different subset relationships involved here.